The formula for the volume of a ball, or the volume of a sphere, is V equals 4/3 pi r cubed. It's a well-known formula. So in this video, I will derive this formula through a slicing method of a sphere or of a ball. Let's see how this goes. So to construct the slicing, I start with looking at the ball sideways, plot the upper arc, and then we have 0 here, we have minus r here, and we have r here. And then this is the y coordinate, and this is the x coordinate. So that would be a side view of only 1/2 of the ball from the top. But now if I take this curve, which I plotted, and I rotate it around, then you can maybe imagine that the whole thing becomes a sphere. So I like to parameterize this sphere. On the circle of radius r, we have that x square plus y square equals r square. And y is the coordinate I'm interested in, so I solve this for y. So then we get y square is r square minus x square, and so y becomes then plus or minus the root of r square minus x square. And now I only plotted the upper part of this curve, the plus part, so I only need plus. So then we have y is equal to root of r square minus x square. So that would be the curve which I have plotted here. So y is root of r square minus x square. And now I do my slicing method. I introduce a little dx, so maybe right here, dx. And then I take the slice here. And now if I take this slice and I rotate it around, like indicated in this arrow, then I do get a disk. I get something like this, which has a certain width. So here, and then this would be my slice. Then I need to know the volume of this slice, and the side length, or the width, is dx, and then this would be the area. So let's worry about the area first. Area A would be pi r square. It's a disk. But now what is r? The radius r is exactly this distance, which is actually my y in my formulas. So it is y. So this is actually pi times y square, where I use my formula. So pi times root of r square minus x square squared, and then the square annihilates the root, and we get r square minus x square. This would be the area written now in terms of x. And so then the volume, the small volume element, dv, okay, would be the area times dx. So I sub in the area formula, pi r square minus x square times dx. So this method is called the disk method, because the volume element which I took out is actually a disk, right? So you can slice down the ball with a number of disks. So that was the hard part. Now I have dv, and I can just integrate it. So then the volume is the integral of dv. So then we integrate, and now the question is, what are the limits of integration? So I have to go back to the picture, and you see here that I have to integrate over the entire graph from minus r to plus r. So let's do that. Then we have minus r to plus r, and then the area was pi r square minus x square, and then we get the dx. Oh, perfect. So that's just a polynomial integration again. The integrand x square is an even function in r. So we can simplify this integral by taking twice the integral from 0 to r of pi r square minus x square dx. So then we get 2 pi, let's integrate this now, r square x minus x cubed thirds between 0 and r. Sub in the r, we get 2 pi. R squared times r is an r cubed minus, and then here we have an r cubed thirds. And if we sub in 0, we get nothing. So then if in the bracket we have 3/3 r cubed minus 1/3, so we get 2/3 r cubed. With the 2 in front, we get 4/3 pi r cubed. And this is our formula as we wanted it. Yoo-hoo!